There are a few problems about being in space. One is the lack of air, so usually you have to bring that with you, and also other things to protect you from the vacuum of space. Also due to that, in space, no one can hear you scream. Perhaps another feature though, and this is a problem for long travel if you want to be in space for a long time, is the issue that there is no gravity in empty space. You would literally just be floating around. And while that can be very cool, after not too much time, you're going to have the issues that your muscles are not working out, they will atrophy, and you'll have very weak muscles. And if you were ever to come back to Earth, you would have trouble standing up. This is an issue that NASA deals with astronauts, and it's a major thing if we're considering sending humans to other planets, and they have to be in empty space for a long time. So we need to find a way of what could we do to simulate gravity in space. Well, we know ultimately that gravity is supposed to be due to having a massive object, so maybe we just take a giant mass with us. Of course, problem is for that is if you want to simulate Earth-like gravity, you're probably going to need a lot of mass. And of course, if you have a lot of mass, that's really hard to send into space. So we need something that can simulate gravity, but doesn't require us moving planets in the process. And there are some ways we can do that if we apply some of our knowledge about rotation. So we know that if a body is going around in a circular path with some velocity, that there must ultimately be some sort of force involved to make that happen. So if I have a body right here, its velocity at that instant is going perpendicular to the radius of that circle or tangent to this circle, and it's going to constantly be deflected, in this case, towards the left. So that way it can move around in this circle. Which means ultimately then there has to be some sort of force towards the center of this circle, which will be then our centripetal force. So let's imagine we have our person standing here. If this person is going to be going around in a circle and standing on this surface here as it rotates, let's consider what other force is acting on him, and this is going to just be out in empty space. So the person will not actually have a weight force acting on them. Again, there's no actual gravity, so there can't be a force due to gravity. And there ultimately needs to be some sort of force that would be pointing inward from this point here, so that way there would be the necessary centripetal force. So what could be acting on this person? Well, if you're actually standing on something, there could be a normal force. The normal force is always going to be perpendicular to the surface you have. In that case, because if this is a nice perfect circle, that normal force is always going to be pointing towards the center. So in this case, the normal force is going to be our centripetal force. And we also know the centripetal force is defined as the mass of the body, velocity squared that you're going around, and the radius of the circle you're going in. So ultimately, we want to actually simulate having acceleration due to gravity that's the same. So basically, we want acceleration of the centripetal type being the same as acceleration due to gravity. And so when we do that, the normal force is going to provide the necessary centripetal force as we spin about. So we just need to do one little bit of work. We can combine our terms for angular acceleration and find that, all right, the velocity you're going around divided by r will give us then the acceleration we need to be just like that on Earth. So one of the things you'll notice is that, okay, you see that as we make our radius size larger, we're going to have to go around in that circle at a greater linear speed. So you make this ring larger, then you have to actually get it to spin faster tangentially. That could be a bit of an issue. On the other hand, we could rearrange this in a certain way. Let's take a look at that. So our centripetal acceleration we can put in terms of tangential speed as you go around divided by r, but we also know about angular velocity, which is the speed that you go around tangentially divided by the radius of the circle you go in. Or, similarly, I can rewrite this as v equals omega r, omega again being the angular velocity. If I plug that into this expression, I can get the angular, or the centripetal acceleration to be omega squared r. So with this setup, omega squared r, our centripetal acceleration, if it's the same as gravitational acceleration, this is ultimately what we want. In this case, we see that the larger the circle gets, the smaller our angular speed will get. So while on the outer edge you might be going faster than you would with a larger circle, you don't necessarily have to have this thing go at a large radial speed. So for a smaller circle, it might have to go many revolutions per minute. With a larger circle, it may not have to do many revolutions per minute at all, maybe much less than a revolution per minute, depending on how big we can make this. This sort of spinning disc or ring idea you've probably actually seen in a few different movies. Most famously in 2001, A Space Odyssey. More recently, it was also shown in the movie The Martian, where on the large spaceship there you have some sort of spinning section that can simulate the necessary gravity. May not be too easy to look at that and figure out how big they're supposed to be, but let's just, for the sake of having some numbers, say the radius of this thing is 10 meters. And acceleration due to gravity is supposed to be 9.8 meters per second squared. And as we mentioned before, okay, we want to have a velocity fast enough to give us the necessary centripetal acceleration equivalent to that of Earth-like acceleration. So how fast do we need to move? It would be the square root of the size of our radius times g. So with these numbers here, you're going to find a velocity that's kind of close to around 10 meters per second, which is basically running speed of a pretty fast person. On the other hand, of course, if we want to do this in terms of angular velocities, so omega squared r equals g, and so our angular speed will be square root g divided by r, and so we'll get an angular speed of around 1 radian per second. And in this case, we can see that the larger the radius it is, the smaller our our angular speed needs to be. So 1 radian per second, or it's going to take around 3.14 seconds to do one rotation, which is kind of fast. In the movies you've seen, it's probably going significantly slower than that. So we could even backtrack and say, oh, I'm looking at this movie, it's taking maybe 10 seconds to go around, or 10 seconds to complete one revolution. I can backtrack and figure out how many radians per second that is, and figure out how big the ring is, assuming we're getting Earth-like gravity in there. So this is a nice way that has come up in science fiction and considered much by other scientists of how you could have an artificial acceleration, or an artificial effect of gravity, the feeling of gravity, even though there's actually no massive body. Remember that ultimately you're feeling the normal force, and that's where you actually feel the weight. If you're in free fall, there might be the force of gravity acting on you, but you don't feel anything. It's only when that normal force is pushing up that you actually feel the weight, and you have to use your muscles to hold yourself up. Now, there is, of course, one issue, though, with this design. Since it's so dependent on the radius, one thing you'll notice that with this sort of setup is that your head is going to be closer to the center than your feet are, which could be a bit of a problem. After all, this point around here, if your head is smaller, then it's undergoing a different acceleration than your feet will be. Everywhere along the way, you're going to have the same angular velocity, in this case, say 1 radian per second. But with that case, your head is a little bit closer, and so it's undergoing a slightly different acceleration than your feet are, and that can be quite disorienting. Now, you can make this issue less of a problem by using a larger radius, so that way the percentage of basically the difference in radii from head to the center, feet to the center, that difference is small enough that it won't matter. But if you had a ring that's only 10 meters long and you're probably about 2 meters tall, give or take, that can be a rather significant difference. So if you want to make this not only give someone artificial gravity, but make sure that they don't get sick in the process and are falling over all the time because they're disoriented, their brain literally will have trouble making sense of things, you're going to probably want a bigger ring, or have everyone just constantly lay on the ground. But that's not exactly a desirable effect.